Well, a warm welcome indeed to anyone joining. Thank you for being here. Get yourself ready with a notebook, a pencil, or a pen. Whatever you choose to write with is fine. This is math from the void, where equations rise like sparks in the night. Our solutions will bloom out of midair. Math coming at you pretty much out of nowhere. One parabola at a time today, that is. So it is the 4th of July in America, if you celebrate that kind of a thing. Here in LA, there will definitely be some fireworks going off. There's lots of hills, lots of buildings. Not everyone can see the fireworks from every other spot in LA. There's some particularly nice vantage points. So today we have a problem that's inspired by viewing fireworks, okay? And this is basically going to be an Algebra 2 level or a pre-calculus level question. It's even a little bit of a physics application. So if you're in physics, you'll get something out of this as well. The situation is that we have a firework, maybe like a grand finale, which is launched from a hilltop platform, and there's a child that is watching from the rooftop or from his window, I guess, of a distant apartment building. It stands 126 feet tall. Here is the equation that describes the height of the firework. All right, we're given some initial conditions, and if you are in a physics class or if you've taken physics, it will be no surprise to you that this is the equation. Now I want to mention something about this negative 16. This negative 16, this is a result of measuring the height in feet per second. If you were measuring this in meters per second, I do want to mention that the number in front there would be negative 4.9. Of course, meters are different from feet, and so that's why. It's kind of like times 3 point something to get to the feet. Okay, well, we have some questions that go along with it, and I also have a fairly artistic and highly specialized quality diagram for this exact situation. I hope you can pick up my sarcasm. The idea is that the rocket is going straight upwards, and I shouldn't even curve it, but we do that sometimes just to show that it does come back down. So it's going to go up, and it's going to come back down at some point. Presumably it will explode at the top, but who knows? I don't really know how fireworks are designed, so we're going to pretend that it's going to explode after some amount of time. That's usually how these things are rigged, right? There's a fuse, and you burn this little wick, and as it burns, it gets closer and closer to creating an explosion in the sky. Some crazy fireworks. Okay, so the question is involving whether or not the kid's going to be able to see the fireworks. He's maybe presumably kind of far away. He's on a very high window here, of 126 feet above the ground. And so here are some of the questions. You can give those a read, try this out. It really is a problem that's focusing on working with quadratic equations, and the graph of which is a parabola, and trying to figure out some important features about the location, or in other words, the graph itself. So give yourself about, 8 to 10 minutes to try to work this out on your own. You can pause the video if you need to. And then when you're ready to look back on how this goes here, you can unpause the video, see how I do it. Okay, let's get started. So what is the maximum height that the firework reaches? That's really important, right? If it doesn't go high enough, the kid's not going to be able to see it. So I didn't mention this, but you'll see it in the question. Assume that the boy can see the firework if it's at least eye level at his window. Maybe he's not able to see above the windowsill, so he can only kind of see the firework if it reaches the height of the window. We've all been there. We've all been small. So what is the maximum height that it reaches? Well, the maximum height is equivalent to finding the vertex height on the parabola. And the time when this happens is going to correspond to something that we call the axis of symmetry. This is the time, or the input value, sometimes it's just the x value, where we get a maximum or a minimum out of a parabola. So because this quadratic equation has a negative coefficient, it's going to be shaped like this, just like if we were to throw something in the air and then it would come back down. That's kind of the shape that it would make, right? In this direction of movement. So let's find out what that is. You're going to have to use this equation from the axis of symmetry. We say usually x equals, but in this case it's going to be t equals negative b over 2a. Now what is this a and b that I speak of? Well, you might be familiar with the quadratic equation in standard form like this. The a, b, and c are just going to be the coefficients. Negative 16, positive 88, and positive 6. Those are the coefficients, a, b, and c. Which means if we're looking for the axis of symmetry using these values, we're going to have negative 88 over 2 times negative 16. And it's good that we have a negative on top and on bottom, not just on top, not just on bottom. Why is that? That's because time needs to be positive. So if we had a negative over a positive or a positive over a negative, that would not yield a positive. We can probably reduce these by 4. We can also reduce this by 8, and we're going to get 11 over 4, which is 2.75. Or if you like, 2 3/4 seconds. So 2.75 seconds later, that's when we reach our maximum height. Now, what is the maximum height? That's when we use the entire equation, h of t, to find the max of height. Now we have the t value that we want to consider. We want to consider 2.75 seconds into the flight, because that's when it's going to reach its highest according to the axis of symmetry. Let's go ahead and plug that in carefully. I think I'm going to use 11 over 4. It's just going to be easier math-wise. So I encourage you to work this stuff out. Don't be lazy. Do not be lazy. 11 over 4, and then plus 6, because the height of the platform that it's launched off of, that's the initial height, is 6 feet. So the total height above the ground is basically however much it's moving plus that initial 6 feet, which doesn't depend on the time at all. That's why there's no t being multiplied to the 6. All right, let's get working. So this is negative 16, and this is going to become something pretty nice here. 121 over 16. Hey, look at that. Super nice. Plus, let's reduce this. We can make this 22. Well, 22 times 11, just multiplying by 11 is easy. You just take the 2, you add them together, put it in between. Straightforward there. Plus 6. So we're going to end up with negative 121 plus 242, which is just double of 121, actually. So if we have negative 121 plus double of that, we're just going to end up with positive 121 plus 6. Oh, look at that. 127 feet. That is high enough. It's a good thing they put it on the platform. Otherwise, boy ain't seen that. So the maximum height it reaches is 127 feet. That's kind of nice. I threw these numbers together with estimates, but I didn't think it was going to be that close. I tried to make it like 135 feet. So does the firework rise high enough for the child to see it outside of the window? Oh yeah. Yes, it do. Yes, it does, if we're using correct grammar. Yes, it does. Because his window is 126 feet high. The firework peak is at 127 feet, which is kind of nice. Let's presume, right? Can we presume that we're going to have an explosion at the top, like at the peak? I know that sometimes fireworks probably fall down a little bit before they explode, but like I said, I'm not a fireworks engineer. I don't really know much about these things. I'm just going to make it nice, mathematically speaking, and have it explode at the peak, which is 1 foot above this kid's window. And so the question is, how long is the firework visible to the child? In other words, like, how much time after he sees it cross the window before it explodes, right? Because you only get that short moment. If you've ever seen a fireworks show, it doesn't last forever in the sky unless they're shooting multiple fireworks. So for how long is this firework visible to the child? Well, we know that it takes 2.75 seconds or 11/4 seconds to get to the max. So the question is, how long does it take to get to a height of 126 feet? That's when the kid can first start seeing the firework. And then we can subtract those times, that little gap in between, that's how much time we have. And it's going to be a split second. I'm guessing it's going to be like, a quarter of a second or maybe even less. How would we solve this kind of thing? Well, we want to know when is the height going to be equal to 126. In other words, solve the equation negative 16t squared plus 88t plus 6 equals to 126. And we can subtract. Yeah, the reason why I picked that height for the kid was just so that this would be a nice negative 120. I didn't really have the other things in mind. Plus 88t equals 0. And this is a quadratic equation that you should be very comfortable with solving. Let's divide everything by a common factor before we try to factor it out or use the quadratic formula or something. Let's divide everything on both sides by negative 8. Okay, solving a quadratic equation is straightforward. It should become your bread and butter. But there are different methods to do it. Sometimes you want to factor. Sometimes you don't want to factor. This would be plus 15 equals 0. And let's see. Two numbers that multiply to make 30 and add together to make negative 11, right? We use the AC method. 8 times c is 2 times 15. And those two special numbers would be negative 5 and negative 6. So we can split the middle term, negative 11t, into negative 6t and negative 5t. And now this is going to factor by grouping. So we didn't have to use the quadratic equation. Nice. The quadratic equation will always work, but if we don't have to use it, sometimes it's better to just factor. Less calculations, which means less room for error. And it also is just a little bit faster sometimes if you can factor it. Now, you need to be able to factor things rather quickly if you want to solve with factoring, especially in a test-timed setting. So let's see, we get t equals 5 over 2, and we get t equals 3. Those are the times when this parabola would cross 126 feet, which sort of tells us something. It tells us that on the way up, it crosses at 2.5 seconds. 5 over 2, I almost struggled with that. 2.5 seconds into the game. Wow, that is not an S, bro. That is more like an S. And then on the way down, if it did come down, it explodes at the top. But if it did come down, it would come back down at 3 seconds. Like if it was a dud, maybe it didn't explode. If it was a dud, then it would cross this same line of visibility at 3 seconds. So which one are we going to use? Of course, we're going to use the 2.5 seconds. And right on the money, I kind of predicted that. I didn't know that would be the case, but when you get experience with math, you get a sense for this kind of thing. So 2.75 seconds, which is when it reaches the peak, minus 2.5 seconds when it reaches the kid's line of visibility at his window. That leaves us with 0.25 seconds, or if you want to call it 1/4 of a second. That's how long this kid has as soon as he sees that window. And I'm sure he's just staring out the front window, just waiting. And as soon as he sees that little firework pop above his line of sight, he has a 1/4 of a second, and then it's going to, boom, explode. Awesome. Kids love fireworks for the most part. If you get to enjoy some fireworks today, be safe, of course. That covers this quadratic situation. That's enough blab out of me. I'll see you next time.